order in which this data is saved, because we save data for performing some operation. So I save this data to perform some operation. Say for example, I want to search. I want to search for 8. How do I search? If the data is not saved properly, then maybe I will have to visit each node. And this will be as good as your linear search. Okay. So linear search, you know that it is time consuming. I will have to, if there are n elements, I need n comparisons. So if say the value of n is 10,000, then I need, if the element is say at nth position, I need 10,000 search operations, and then I will get my whatever key element I am searching for. So then there will not be these trees will not be of any use then. Okay, so we have something called as binary search tree. Okay, so uh, if we use binary search tree, then searching or say insertion or deletion of elements can be done efficiently. Okay, so there is a good definition of binary search tree on the next slide, but we will just see this slide what this definition means. So for every node x, so for every node x, all the keys in the left subtree, all the keys in this left subtree are smaller than the key value x. So all these nodes here, they will have a smaller value. Okay, they will have a smaller value compared to x. And the keys in the right subtree are larger than the value of the x. So whatever are the elements here to the right of the x are going to be larger than larger than x. Okay, so it's something like this. There is a element x here. All the elements which are smaller than x will be on the left side, and all the elements which are larger than x will be on the right side. So this is your binary search tree. For example, say I have 9 here, I have 3 here, and I have 14 here. Now this is a binary search tree. Why? Because it is following the definition of binary search tree, which says the element on the left should be smaller than the root. The element on the right should be greater than the root. Okay, so this is a binary search tree. Whereas I take another example, say a tree something like this. If there is 7 here, there is 9 here, and say there is 4 here. Now, is this a binary search tree? No, this is not a binary search tree. Why? It is not satisfying the definition. Okay, because this root element should be larger than the left element, whereas here it is 9, which is greater. So this is not a binary search tree. Okay, hope you have got some idea. The clearer definition according to your textbook is this, which is displayed on this slide. So a binary search tree is a binary tree which satisfies the following properties. Okay, your binary tree is your binary search tree is a binary tree which satisfies the following properties. What are those properties? Each node has exactly one key, and the key in the tree are distinct. So if there are keys, meaning the value at the node. Okay, when I say key here, it means the value which is at that particular node. Okay, so the first point means there is no repetition of keys. Okay, that is what the first point says. Then, because key is what, it is some unique value. It is something like your USN. So obviously there will not be two students with same USN. There will not be two students with the same roll number, because that is the key which is needed for identification. Another example of key is your bank account number. So there will not be two people with one bank account number. So that means the keys should be distinct. Okay. Then the next point says the key in the left subtree are smaller than the key in the root. So if this is your root, if I have a left subtree here, these should be small. That is what the second point says. The key in the left subtree are smaller than the key in the root. So subtree, whatever we have here, whatever elements we have here, should be smaller than whatever is there on the root. Okay.
Why is
Then
that?
Sorry, voice. You are not able to hear. Now is it better?
Yes, sir.
Okay, we'll hold it like this and speak. So uh, we are defining a binary search tree. We are looking at what is a binary search tree. So the first point says all the elements should be distinct. Second point says whatever is there in the left subtree should be smaller than the root. So any number of elements which are there here to the left should be smaller than the key. Then whatever is there on the right subtree should be larger than the root. So there is a right subtree here. These should be larger. Okay. All the elements here on the right hand side should be larger than the root. Then the left and right subtree are also a binary search tree. So even this is a binary search tree, even this is a binary search tree. So that is the definition of this. This is something to do with recursion. Okay. It says the left and right subtrees are also binary search trees. So even this is a binary search tree, even this is a binary search tree. Okay. Hope the definition is clear. Next, you will see which is a binary search tree. So this is an example of a binary search tree. Okay, because root is 6, all the elements on the in the left subtree are smaller than the root. Okay, and all the elements here on the right hand side are greater than the root. Okay, so 8, if you see, 6 is smaller than 8. So it means whatever on the right is greater, whatever on the left is small. Left meaning it should be all elements, not only this element. It should be all elements. So 2, 1, 4, 3 are smaller than 6. Then the definition, the last point said, you can see the last point once again. The left and right subtree are also binary search trees. So left side I have this particular tree now. This is subtree in which root is 2. So this also should follow the definition of binary search tree. So it is very correct here because 2 is greater than, or whatever on the left hand side is small than the root, whatever is on the right is greater than the root. Then this is another tree. So here this is your root, whatever on the left is small, whatever on the right is big, right? There is nothing, so that's fine. So this is an example of your binary search tree. If you see here, there is uh, 2 which is smaller, 8 which is greater. So till here it is okay, it is satisfying the definition. But the last point said even the subtree should be a binary search tree. So you come to this particular subtree, you see there is say element which is 4, and then there is element which is 3. So this is satisfying the definition. But here if you see this 7, this 7 with this subtree it is sounding okay, but if you see the entire thing, then element 7 cannot come here. On the left hand side you cannot have an element which is greater than the root, and thus this is not a binary search tree. Okay, getting it? It's very simple. You have a root node, whatever on the left should be small, whatever on the right should be big, or say large. Here now it may also it may so happen that it is not that we have some set of numbers like 5, 3, 7, 2, 4, and 8. So if we have these numbers, it is not that the tree will be same every time. It depends on in what sequence these numbers arrive. Okay, in what sequence these numbers are given. According to that, the tree will be created. So if you see both the trees are binary search trees, but then they are not same. The numbers are same, the values in the nodes are same, but the trees they don't look same. Okay, so this is also a possibility. Both are binary search trees. Now next slide will see something which is very important. In your exam you get a question saying create binary search tree which is also called as BST. So they say create a binary search tree with following keys. Okay. So they give you some keys and they ask you to create a binary search tree. So they give elements something like this: 4, 2, 3, 6, 5, 7, 1, something like this. Okay. So this is also a sure shot question in your exams, and there is a lab term work also which is doing this. So they give you elements something like this. Now, what happens is we'll have to draw a binary search tree. Okay, we'll have to draw a binary search tree. So any element which appears first in the sequence, that becomes root. Whatever is the element first, that becomes root. Now I start drawing a binary search tree. Now where do I place this 2? First element is root, as I said, it is 4. Okay, first element is root. Now next 2 has arrived. So where do I place 2?
Left side.
To the left side, correct. Because that is the definition of binary search tree. Whatever is small should go on the left. So I put 2 here. Okay. Next element which has arrived is what? 3. So where do I place 3? To the left. Okay.
Left
From
side.
every time I start from the root. Okay. I have to place to the left. So left, if you see, there is another tree. So left there is left there is already a subtree. So again, I should consider this as root and compare the element which has arrived now. So 3, is it small or larger than 2? It is larger. So larger meaning it should go at which side?
Right side.
Right
The
side.
right side. So it comes here to the right side of 2. Next element which has arrived is 6. So again, I should start comparing from the root. You should not compare from the current element. Otherwise, the tree will become a linear array kind of thing. Okay. So every time you should start from the root node. So 6 has arrived. 6, is it larger than 4? Yes, it is larger. So it comes on the right hand side. I draw 6 over here. Then 5 is arrived. So I should compare 5 with the root element. It is bigger, so it comes on the right. I compare with this element, it is smaller, so it goes on the left. So I draw a node here, which is 5. Next number which is arrived is 7. So I compare 7 with 4. 7 is large, so it comes on the right. I compare with 6. 7 is large, it comes on the right. I draw 7 over here. Then 1 has arrived, which is the last element. I compare with 4. Then I compare with, meaning it is small, so I compare with 2. It is small, it comes over here. I draw 1 over here. Okay, so this is your binary search tree for the given elements. It is not that every time you get a tree, a complete binary tree, something like this. Okay, you may get the tree in any order, as you had seen in the previous slide. It can be something like this also. You may get the element something like this also. It is not that every time you will get a complete tree, something like this. Okay, so you may get it anyhow. Is this clear? Now, in your exams, what they do is they ask you to create a binary search tree. They give you this sequence, and then they ask you to also do the traversal, that is in order, pre-order, and post-order traversal. So, can somebody tell me the in-order traversal of this tree? In-order traversal. So, what was in-order traversal? I should visit left first, then root,
Root.
and then right. So, what is the in-order traversal of this tree?
1, 2, 3,
1, 2,
3,
3,
4,
4,
5, 6, 7.
5, 6, 7. So correct. This is the in-order traversal of your binary search tree. With this, also you see that there is one special thing about binary search tree. That is, if you traverse the elements in in-order traversal, you get the elements which are sorted. So if you see, these numbers have come as sorted. Now what I have done, I have just performed one operation which is in-order traversal. So this is the beauty of this binary search tree. In-order traversal you perform and you get the numbers of the tree or nodes of the tree in sorted order. Okay. And then
Okay.
there is another special. Yeah. Somebody is asking something.
No, sir.
Okay. Okay. So another specialty is if you want to find the smallest element, it will be the leftest node. So exactly the leftest, whatever is at the left side of the tree, that will be the smallest element. Okay, leftest leaf node. And then whatever is on the right side will be your max element. Then similarly, you can perform pre-order and post-order traversal also of these trees. So they will give you this question saying that create a binary search tree with the following keys. They will give you some keys, and then they will ask you to perform in-order, pre-order, and post-order traversal. There will be some marks for drawing this tree as well. Okay. Any doubts here? Anybody has any doubts?